Good afternoon. Ooh, kind of loud. Okay, being the presiding officer at today's meeting after last week's election, thank you all very much. And thank you, I am Bill Breezy. I'm second vice president, and this is the Engineers and Architects of Hawaii. If you're in the wrong place, I think there's another conference room on the other side, and you didn't pay enough, I don't think. But first on the agenda is to introduce guests. I think we've got a few guests. So would you kind of tell us who you are and what you do?
I'm Bob Burke. I'm an environmental scientist from Oceanit.
I'm his daughter, Katie Burke, and I'm studying architecture in New York City.
Second time I've been here with Dave Martin. I'm also from HECO.
Hi, I'm Anna Groon. I'm with Aaron, a guest, and I work with the same firm that Aaron works for, West Union Elsinore. I'm an architect intern over there.
Well, thank you all very much for joining us today. I don't think we have any business notes or anything. Anybody have? Oh.
Dues are $50 per person.
Per year. So when are the dues due? Today.
You can't leave the room.
Our year starts
And we're accepting new members, right? So all guests can sign up and join as well. So that being said, I'm going to turn this over to Aaron.
We have a joke.
Oh, joke for the day. Oh, that's right. I didn't look at my agenda. Sorry, this is my first time. I'm just getting used to this. Does anybody have a joke? Sure, we'd have one at the end of the table over here. We always have a great joke. Sure.
Today's my birthday. I'm 86 years old, and this is a good occasion to explain why I do this, why I try to come up with these stories. My grandfather never graduated from high school. In the month or so before graduation, the principal informed him he was the head of the class. He would have to get up in front of everybody and give a speech as the valedictorian. That's not going to happen, thought my grandfather. A week before graduating, he dropped out of school. So although he had a high school education, he never had graduated. And I come up with these stories thinking how proud of me my grandfather would be. That's my motivation. The story today is from this little town in Iowa where I grew up. The fellow decided he should be the new county road commissioner. So he got up on his soapbox at the appropriate occasion, said we need a new road commissioner. If I'm elected, I promise to do a good, honest job. The incumbent pays the road to his farm. Somebody in the back of the crowd said, "Yeah, that's right. Let's re-elect him. He's already got a paved road to his farm." Yeah.
Okay, we got a very exciting program today, repair of post-tension structures. Boy, do I hate post-tension structures. One of my projects was post-tension, and we made very careful to make sure that everybody who's going into the building x-rays the slab, and so that all the tendons don't get hit. Well, we had x-rays done, and the coring guy put the x-ray down and found out where to drill and got halfway through, and he put the x-ray upside down. So you got to make sure it says this side up so that that doesn't happen. Okay, well, Aaron, take it from here. Thank you.
Cool, that's a good one. I'm going to talk about repairing post-tension structures. As some of you know, it's kind of a pain to do. It gets expensive, and it's these kind of things, other trades have to be careful when they come back and modify things. This is work that I do fairly routinely at WJE. Our company focuses on repairing stuff, so we get involved in this kind of thing a lot. I'm going to show you some examples from some ongoing projects and stuff that's recently done. First off, though, why post-tension something in the first place if it's such a pain? Basically, what it allows the concrete to do is perform more efficiently. Concrete's weak in tension and strong in compression, so the purpose of these cables within your slab is to keep the concrete theoretically permanently in compression. So when you load it in a beam, instead of creating tension, you relieve the compression that's already in there. It allows concrete to be longer spans and thinner members and generally nicer. So that's how that works. This effect is accomplished in various ways. You can have prestressed members, which are typically precast. These kinds of things are made in a yard somewhere, and the way those are put together is you have a cable that's stressed, and then you pour concrete into the form, and then when the concrete gets strong enough, you release the cable, and it's bonded the whole length. I'm not going to talk about this kind of thing because the repairs are relatively simpler. Post-tension members are kind of the opposite. You put the concrete first with ducts and cables in there. Then when the concrete gets strong enough, you can stress the cables, which transfers the compression to the concrete. These fall into two categories, bonded or unbonded. I'm going to be talking about unbonded systems because they're way more common and also harder to repair, I guess.
Could you define bonded?
Sure. Bonded basically refers to the concrete in general being adhered to the steel. So in that kind of system, if you have a cable that rusts through or something, the effect's pretty local. So you lose your cable where it's rusting, and then the bond to the concrete makes it effective away from that area. In unbonded systems, you'll have this tendon running multiple spans in your structure, and it's not attached to the concrete. So if it breaks anywhere along its length, you lose the effect for the whole span. So it's a little more of a significant thing when those types break. So this is a picture of what a bonded post-tension system looks like. They have these metal ducts in your slab. What this picture is a parking deck. You're looking at the top surface of the deck where they dug out some of these. And then if you breach the metal duct, there's a cable inside, and the space between the cable and the duct is crowded with the cementitious stuff. Unbonded systems, basically it's a sheath with something to prevent the bond, like a grease or something like that, and then your metal cable goes inside that. This particular one is from 1972, and you can see it's got this ratty paper stuff on it, and you can't really tell if there was grease or not to begin with. I have an example of that here. This is kind of how it was done in the earlier days. What was found in subsequent years is that these things corrode and break, and they're problematic. So since then, improvements have been made. This is a picture of a new tendon. They come in big coils like this. It's basically a continuous plastic sheath with no seams on it, and it's filled with improved grease that doesn't get emulsified over time. And kind of an intermediate system, I only have a little piece of it, but is this gray sheath. If you look at it closely, there's a lap in it. So it's formed by a plastic sheet that's lapped over and welded on itself. So that's kind of halfway between the old and the new. But once in a while we'll see those too. This is a picture of a new cable with its sheath removed. You can see lots of nice goopy grease on there to protect it. This slide kind of explains what I just said, the evolution of these systems. And basically the whole direction is improved corrosion protection. And it's important because the strength of these cables is a lot stronger than your conventional steel. And if you lose a little bit of it, it's more significant compared to if you lose a little piece of your rebar. So this is the paper one, and then they went to plastic sheaths with gaps between the anchorages, which would corrode. And then in 1985, the Post-Tension Institute recommended this system, which is completely electrically sealed, which is what's preferred today. And Yeah, the electrically isolated basically means all the metal that's structural in there has no electrical connection to anything else. So the whole system is insulated. Not necessarily galvanic, but just corrosion in general. A lot of time, what happens is this zone here is problematic because you put these cables in before they're stressed, and you have these anchorages, there's some sheathing, but when you pull the cable, it stretches like 6 or 10 inches or something. So you need to have some space for movement there. So the electrical isolated system protects that area too. The material itself in the cable, back in the 70s, it's the same ultimate strength, 270, as the new one. Same size, dimensions. The old ones are called normal relaxation, and the new ones are called low relaxation. And basically, relaxation is referring to under sustained stress, the metal stretches. So after a few years, the state of stress in your metal will be less just because it's stretching out a little bit. And then I talked about the sheathing. The old ones are paper and the new ones are polyethylene. So this kind of gives some numbers to that relaxation concept. The normal ones at 80% of ultimate stress, you'll lose about 12% of your stress. And the newer ones, you'll lose about 4.5%. So it's a material improvement that's been made since then. The effective tension on one of these things is about 27,000 pounds. So that's why when somebody drills through it, it makes a nice pop. And when they break, they can blow out the inside of your building or through slabs and stuff like that.
What would be the cross-sectional area on 27,000 pounds?
These are half-inch diameter, but it's not in perfect circle because there's 7 little wires.
So it's about a third of an inch in that metal.
Yeah.
So that's 100,000, well, 70, 80,000 feet.
So the basic problem with these things, as I said, corrosion. Highly stressed metal is more sensitive. Detailing in the old systems doesn't really take into account corrosion enough. And sometimes you get placement issues with the tendon going too close to the surface and being exposed too much. And then there's the man-made damage. So I'm going to talk a little bit about what you'll see when there's a problem with one of these things. This one is the side of a building, and where this little pocket is, there's this little stub sticking out. And this one's only a couple inches, but these things can jump out a few feet. In certain cases, it depends how long the cable is and how straight it is. It's basically recoil. So if you cut the thing, there's all this energy stored in it. So it's like a rubber band. It tries to pop backwards.
So that one was
Yeah, this was a broken one. I think these two ended up being also with issues.
What building is this?
This is in Aiea. I think it's Century West. It's a residential
How close
building.
in space were they?
These were about, I'm thinking like between 2 and 3 feet.
So there was the cables that are not shown there.
Yeah. So I would mention before the meeting, these systems are pretty redundant. So if this one breaks, you got one here and one there. So it's not like your building's in grave danger or anything. So if you catch these as maintenance and fix them and fix the problems that are causing the corrosion, it's generally not a big problem for everybody as far as like collapses and things like that go. This one is a parking garage in Waikiki. This is a PT slab, and there's this bulge in the bottom of it, which was slathered with epoxy and by their maintenance. And basically, we found the cause of this one was this wall. It's below the water table, so you got seawater seeping in, which caused lots of corrosion. This is the top side of that slab after we took out everything that needed to be done for the repairs, and they had a bunch of broken ones here. You can see 3 there, 4 there, and there was a couple broken ones going this way. So a little thing like that, which doesn't look totally alarming, can turn into something bigger if you have a big driver of corrosion in the area. This is a lanai near University. These pieces popped up and they called us to try to figure out what's going on. And the building had these paper wrap tendons, and right here is the high point because the lanais are kind of cantilevering over the edge, so you want your reinforcement as high as you can. So they were covered by about between half an inch and 0 of concrete. and you can see it's just bare concrete, so they didn't have any protection at all. So
Why do they pop up like that?
when you release the tension, the thing recoils back.
Okay.
So if you're at like a deviation in profile, or what also can pop these up is just simple rust expanding.
It's like a kick of a rifle butt then.
Yeah, basically.
Okay.
So sometimes you'll see little spalls on your decks like this, and that can mean post-tensioning issues. This is an opening in a slab we did, and we cut off the sheathing to see what the cable looks like. This one's bright and shiny, and this one's got some rust on there. The contrast doesn't let you see that too much. But basically what happens is once water gets into these plastic sheaths, they're kind of captured there, and they'll find the low points and puddle there and cause problems. But if you have it sealed off, it stays good. So I'm going to go through a couple ones that are good candidates for repair. This one you can see it's got a wire kind of missing there. So it's at least partially lost its stress. This one's kind of the same deal. Sometimes when you take them up, there's no attachment at all. This one has some emulsified grease in it. The old greases they used weren't durable. They'd get dry and crumbly after a while. So that's also...
As you go along, could you mention if you were redesigning this today, what would you do to prevent this?
Sure, yeah. To prevent this, for one, this one was fairly close to the surface, so you'd want to have it covered a little bit more. This system is that intermediate system with the lap sheath. The new systems have a continuous plastic tube, so there's no path for water to get in on those. And then the newer greases are improved also. This one, sometimes they get big and basketing out because once you start losing them, the wires kind of get frayed like
Did
that.
the concrete just explode on its own, or was that dug out?
It was almost there. You had little chunks on top. So the anchorage zones, as I said, are kind of critical parts. These are a couple that we've repaired. Basically, they clean them off and epoxy coat them. These ones were. This was that lanai building with the two spots. We found a lot of these anchorages. They were still fine holding the stress, but the metal plate components were rusting and kind of spalling off the concrete. So we went and did this repair. This one doesn't involve retensioning anything. It's just cleaning and putting the concrete back. And they can get looking pretty ratty like this one. So you can see that guy is fairly well rusted. But these, I mean, they're still there holding the stress. So functionally they're okay. What optionally can be done is just clean them and coat them and cover them back up. This particular one was in the end of a beam with like 50 ends. And this was only happening to a smaller portion of them. So you got to kind of consider what your situation is and how redundant the system is. So for isolated break, you may be able to accept the loss of a tendon. More commonly, you just restore what the original designer put in, just because the cost of engineering fees approaches the cost of actually doing the repairs, so you might as well just fix it. The procedures: you remove the cables, you demolish the area near the break to make a splice. You insert a new cable, you assemble splices, new sheathing, apply tension, install sleeves around your splices, and patch it up with new concrete. And you want to coat the outside of the concrete too to prevent water coming in. So I got some pictures of that. This basically is a cable that broke. This is the splice here, and this is where the stress is applied here. There's a special device that allows you to do that. Normally the stress is applied at the ends.
This is the retention.
Yeah. So this cable was broken. There was no tension in it. So from there to there is basically new steel and a whole new assembly.
What do you splice?
I'll show you in a second. The splice is basically a barrel-shaped thing. It's kind of like the Chinese finger thing. So there's these wedges that grab the cable and prevent it from pulling out. Basically, this little component is called a dog bone because it's sort of shaped like that. And you have a cable that comes in this way, and then it's anchored there. And then your cable coming from the other direction comes in this way, and it's also anchored here, but it allows you to jack against it. Because sometimes the ends of the cables are obstructed from facades or whatever. So a lot of times it's easier to do this somewhere in the deck. So I'm going to show you some videos of what this looks like. So the first thing they do is they set all the wedges, and then they apply a stress to it without finally locking it off. And that's just to set all the components and make sure everything doesn't move unexpectedly. This device here is a hydraulic jack. You got a pump here with a gauge that measures your pressure. And this little guy has a wedge that grabs the cable here, and it's pushing against that dog bone piece there. So in doing that, it pulls the cable through. It's important to watch how much stress you're putting on it, because if you stress it too much, you'll break it. And if you don't stress it enough, you're not getting your effect. So that's what it looks like just to set it. And he's going to take that guy off. The next step...
You ever pop one of those cables when you put some tension on?
Yeah, it happens. What happens in that case is you pull it. A lot of the cable's still embedded, so it may have issues down the line somewhere. So he'll do that, and then it'll just keep pulling out. And if there's an issue somewhere down the line, what they do is they take the cable and pull it out of the hole and measure how long it is, and then they go dig where the issue is and splice it again. This can happen a few times. So the next thing they do is install wedges on the cable. And the wedges are little hardened steel things like this. You can pass them around. They've got teeth on the inside of them to grab the cable as it pulls in. So he's just sliding it on there. And the wedges seat inside of a little hole inside the dog bone piece there. So
Shouldn't. Just cut that off.
So it's important to make sure those things get tapped in nicely. Hammer there. And then the next thing to do is set up your hydraulic ram to the final test. So he's making sure he's got a connection there to the cable.
Just 2,000 gauge reading, I forget whatever that is there, but that's just to seat the couplers, the wedges.
Then the next step is applying your stress
If you do that, then at least you have to
make the cable do what it's supposed to. So he's going to be looking at this gauge here, making sure he gets enough tension on there. For this particular cable, it was kind of a long run, so what he has to do is jack only goes a certain distance. So he pulls it and then resets it and then pulls it again to get the final amount there. Just resetting the lock on the jack side. So these cables can stretch quite a bit, and it's important to take a note of how much they stretch when you're doing this, because if you expect it to stretch 10 inches and you only get 5 inches of stretching, and you have the load you expect, something's going on there, and basically it means you're snagged on something. Or if you get too much elongation, it means something's slipping, and you have to kind of diagnose that. The gauge is in PSI, which converts fluid pressure to the unit conversion, converted to stress. step is measuring the elongation, like I told you. The way that's done is, before he does his tensioning, he makes a mark on there, and then afterwards he measures the change in placement for that mark. So,
How much travel do you measure?
it depends on the cable length. It's
Anywhere from 1 to 5 inches?
could be quite a bit more than that. Usually a 60-foot cable is about 3 inches or so. So it can be twice that or more easily. It's part of the procedure for doing this sometimes is you take the old cable out, you measure where it is to find the location of the break, then you have to put a new cable in. And the way that it's done is you have to push the new cable through the old hole. So I have some fun videos on this showing that it's easier said than done. Sometimes these guys have to be kind of creative using things like the Chevrolet anchoring device here. So when he's using his jack in the opposite direction to push that cable through, the back of it has to react against something. So a lot of times that's the edge of the hole in the concrete, but sometimes it needs to be something different. For this one, it's a little lesson in buckling. This cable kind of deviates that way. I'll show you what was going on in this picture. So this takes a while because if you have to push through like 30 feet of cable and you only have a jack that travels 6 inches at a time, you can be sitting there stringing it through for quite a while. He's getting his jack set up so it can react against something. This cable's getting pushed from here to the hole there. I don't know if our resolution is going to let us see it though. He's pushing on it. The buckling length's too long, so the column buckles. So it can buckle either way. So if you brace against the other side, it buckles that way. So the solution in this particular situation was to decrease the buckling length. So he put a piece of wood in the hole, parked his truck on it, and then this length got shorter. So yeah, these guys, you never know what you're going to find, and they have to be smart and willing to adjust their plan with whatever comes up. Because a lot of times you pull on a cable and it's broken in 3 other places and stuff like that. So this is an example of that. I think the first break splice was here, and then they had to go here, 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 there to kind of chase it down. So sometimes you apply tension from the outside of the building, which is using an anchorage like this. I'll show you what that looks like. Kind of the same deal as before. Might be a clearer view of it. This little wire piece here holds a wedge that's held in there by springs, and that's where the jack holds it, and then there's another wedge in there. You can see the pressure on the gauge increasing.
Okay, wait, I gotta pull again. Why did it fall off?
He's resetting the jack. This jack has limited travel, and these cables are expected to elongate longer than the travel of the jack. So he has to jack it, lock it off, and then reset his jack, and then pull it again to get the. Yeah, that was normal. Yeah.
There we go.
And it hung on because it has this jack on this wedge on this side. And they don't have to do anything special to lock the wedges off. Just the stretch of the cable will pull those 2 wedges into the seat, and they automatically lock.
When the jack moves out like that, everything's working.
Yep, exactly. So after they stress the tendons, there's a tail hanging out. And this is just a picture of the guy cutting it off with a wheel. This is a different job site. This is the man-made damage. This pipe needed a hole through the slab, and they cored it and then cut these two tendons here. So check before you dig, I guess, is the lesson here. Yeah. A lot of times when we scan slabs for people, we'll just mark right on the slab so there's no question. Also, when you're doing these repairs, if you don't have experienced people that know what they're doing, when they're preparing the area, see how they nicked the two wires there? That was happening when they were saw cutting the edge of this square here. So yeah, you don't want to do that. This picture is when they were making a new anchorage for their cable, and they put this concrete in and then stressed it the next day, and that didn't work because the concrete didn't have time to attain its strength, so it just kind of crushes. This one I thought was kind of interesting. That this is looking down on a lanai in a high-rise. This is your railing here, and there's an anchorage out here. And then for some reason, the existing cable came in and went on a curve like this. And the problem that caused was when you pull on a string, it tries to straighten out, right? So there was a high bearing stress here that caused their concrete to pop out. This one was kind of exciting. The wedge had this crack in it, and it broke when they were stressing it. And when these things break inside concrete, they have a bunch of recoil and they can throw pieces off. But when you have a length of 12 feet exposed with nothing restraining it, that cable whips out and smashes into things. And people can get hurt doing this. So that's my experience with that. Nobody got any injuries that day, but it was pretty hair-raising. Other considerations with PT structures, if you have permanently compressed concrete, you don't expect it to crack, right? However, post-tension concrete gets smaller with age. It dries out. The constant compression of the concrete causes the concrete to eventually change dimension and get smaller. And these dimensional changes can get restrained by other structural elements. So if you have a PT slab supported by shear walls, the shear walls are going to be really stiff, and then the slab's going to be trying to shrink. So you can get some cracking associated with that. Usually those aren't really structural concerns. Repairs for that kind of stuff is more architectural in nature, but it's good to know about, I guess.
What shrinking are you talking about in a 60-foot slab?
Off the top of my head, I probably couldn't tell you, but it's not a huge amount. It's probably less than an inch.
What's this little wedge thing made of?
Yeah, it's steel. Yeah, it's a super high strength stuff. They're heat treated, so they're real brittle and hard. I think they're probably even stronger than the PT strands. One of the advice of the senior guys in our company, you got two kinds of concrete. And you got concrete that has cracks and concrete that's going to crack. So that's our thought on cracks. I kind of talked about the adjoining parts of the structure. If you have a PT structure with cracks in it, usually you can tell by where the cracks are and how they're oriented with what's in there, what their cause is. Usually they're not attributed to structural deficiency. Running out of time, I'm going to open it for questions, but these last few slides are about how the losses are calculated. So when you're designing something post-tension, you're depending on a certain amount of compression being on the concrete for your structural performance. But how much you have is kind of hard to exactly determine because you have the steel stretching, the concrete creeping and getting smaller and shrinking because it's losing water, and the wedges seat in and you lose a little bit of tension, stuff like that. So there's some obligatory equations because I'm an engineer, and a graph. There's another graph. Okay. I'll open up for questions. Anybody curious about anything I said?
Can you get stainless steel cable?
I haven't seen stainless steel PT cable. I think there may be limitations on the strength, and relaxation kind of issues. I know when you have cable exposed in corrosive environments, you can get galvanized cables. So you'll see those for parking barriers and stuff like that. Neat idea. Okay, thank you guys.
Well, thank you, Aaron. You didn't address, one of the projects I'm working on right now is at IHS. We're trying to create a roof garden on top of the roof, and in order to do that, we have to extend the stair up, and there are no less than 30 post-tension strands going through the roof of that stair. So right now, the contractors out there are trying to chip away without making the strands be able to put the dead end in before they detension one side so that they don't have to go back and do all the retensioning.
Sounds like fun.
Anyway, in the engineers and architects of Hawaii tradition, you have a certificate of appreciation, Aaron. So
Thank you very much.
Thank you very much.